Hi there, in my previous video I designed a combination single board computer and H8 CPU board that used the 8186 CPU. Now that is a CPU with a 16-bit internal data bus as well as a 16-bit external data bus. So you address your memory, in words of 2 bytes each. Now there is a counterpart to that 186, which is the 188. And just like the 8086 had its 8088, the 186 has its 188, and that is the same CPU but with an 8-bit external data bus. So you can still do your computations and such internally at 16 bits, but it gets serialized down to 8 bits when you go out to memory and I/O devices. And while I was working on that video, I saw this listing here come up on eBay, and I just couldn't resist. I had to buy this thing and try it out. What this is the OEM-188, which is a single board computer based on the 8188 chip. So that is that sort of 8-bit external bus little brother to the 8186. And this was actually a commercial product back in like 1987 or so. And I came across an eBay seller who had a couple of these. He'd been sitting on them for a while. He'd bought them from some warehouse that had acquired them as leftover stock from the manufacturer. But this board here, you could have bought this and put it into a commercial product as an embedded controller back in the 80s, but it was also part of a radio electronics article series called the RE Robot, the Radio Electronics Robot. And I don't know about other people on this channel, but I sort of religiously read radio electronics in my youth. I learned a lot about computers, a lot about electronics by reading that magazine. And, this would have been one of the things I would have wanted to build. So they had schematics, theory of operation. It's all out there. There's about 10, 11 articles on the RE Robot, and about 3 of those articles are on this particular board, which you could have built yourself, up from artwork and parts, or you could have bought it. A company called Vesta Technologies made these. Now, Vestatech's website, as far as I can tell, it doesn't go anywhere anymore. I did find it on the Wayback Machine, and I found, sort of legitimate stuff all the way up until like 2017, going back to early 2000s, but nothing really reflective of the era of this OEM-188. So what I'm hoping by making this video, I'm going to keep this a relatively short one today, just give this thing a try out, but some people out there might have some of these boards, might have some documentation or some ROMs or some discs or a manual or PDF or something that goes with this, because I could use a little bit more information. So if you have an OEM-188, or you have the Radio Electronics RE Robot, or you just happen to be a collector of obscure technical literature from the 1980s, please let me know, because I'd like to collect some more resources on this board. There's enough information out there with the radio electronics article that people could actually build these themselves right now if you wanted this controller. So let's take a little bit closer look at this thing. Okay, here's a close-up of the OEM-188 board. So right here, Vesta, made in the USA, I think it says 1985, revision 10. You've got the 8188 CPU right here in the middle. This is actually an N8188, so it's not the ADC188, it's just a plain ordinary 8188. Probably the 8 megahertz one, and it has a date code copyright there of 1978 on it. So you've got the CPU, you've got a bunch of static RAMs down here. I believe these are each 8K static RAMs. 8 of them together will give you 64 kilobytes of RAM. Now this CPU, of course, it can address up to a megabyte of RAM. They do have some breakouts here for some extra address decoding there, and a bunch of little jumpery pin things up here. So I think you might be able to put bigger RAMs in here. It'd be interesting to find out. Over here you've got the ROM. So the first ROM is always the BIOS ROM. Now this thing does appear to have a standard PC style Int10 BIOS. And then on top of that, there would be an application ROM. So right here we have a 4th ROM. And the seller of the board actually gave me a bunch of additional ROMs. So we've got some additional versions of both the BIOS and the 4th ROM. So we've got a 4th 83 ROM, Here's another one, fourth from 1986. Here's an OEM BIOS from 1986, so a little bit older BIOS. But the other two sockets, I think you would put your fourth code in them. So, you know, there's a couple things here that say salting out. You know, I dumped the ROM images and looked at the strings in them, and it does seem to be a bunch of fourth code in these two ROMs. So these would have been stuck in those two positions there. Now this board also has an EEPROM programmer on it, and I think it just uses one of these sockets here as the EEPROM programmer in it. You put in your unprogrammed EEPROM, so you would have to erase those with UV light, so you erase it with your UV light. You stick it in there, and then you type in the program statement, and you can program some of the screens. Now that's how fourth's unit of source code is the screen. You would program some screens from RAM to EEPROM. And then your program would be permanent. So you've got room for, like I say, 2 program ROMs or a program ROM and an EEPROM that you're programming. This up here, you know, it looks like it's kind of the form factor for another ROM, but it's actually an 8259, a interrupt controller. And the radio electronics literature says that even though the 8188 had a built-in interrupt controller, they went with the external one for DOS compatibility. So they were actually trying to make this thing text mode DOS compatible, and we'll see that in a little bit. So that gives you sort of this part of it. Over here you have an expansion header that, you know, breaks out a bunch of signals. You'd have an expansion bus. So up here we have your UART, and the UART comes out over here to a 3-pin header that is your serial, which can go out to your external, your terminal or whatnot. And over here is the floppy controller, the Western Digital WD1770. And it comes out here to this 34-pin header. And right alongside that 34-pin header is a 4-pin power header. It's got 5 volt, a couple of grounds, and a 12 volt. And the 12 volt is just simply a pass-through from the input power. So the board itself is all 5 volt. 5 volt used to power the board. And then 12 volt comes from the input power, pass through to that floppy connector. So you can simply hang your floppy off of this data and control connector and this power connector. There's also this big thing here is some kind of a NiCad battery pack. So I think one of the things you could do with this is you could develop your fourth programs in RAM, and then, you know, work on them and not have to commit them to ROM until they were done and ready to go. So that would make the battery backup really useful. There's also a real-time clock in here. I'm not sure exactly which one of those ICs it is. It should have a crystal nearby. So, well, the third crystal is not jumping out at me, but I'm pretty sure that somewhere on this board there has to be a 32.768 megahertz crystal for the real-time clock, as well as the real-time clock itself. Okay, I think it's time to do a quick little demo. So we have everything ready to go here. I have the board hooked up to power coming in off of my my power supply. I've only hooked up the 5 volt. We don't need the 12 volt. And I have the serial comes out here via this cable, and this goes into my Microsoft propeller serial terminal. So just a VGA dumb terminal. And I can hit kind of Control F10 here, and you can see the terminal settings. I've got the terminal set for 9600 baud. That should all be good to go. And I have a null modem adapter in here as well. Okay, so let's go ahead and turn it on. So the first thing it does is it tries to access the floppy. There's actually a little floppy LED there blinking. I don't have a floppy, so it's not finding anything there. It takes it a few seconds and then it times out, and then we get our sign-on message, which is this Vesta 4th 183. So in this case it booted directly into 4th. If there would have been a floppy, and if there would have been a viable boot sector on that floppy, then it would have tried to boot from the floppy. And we will actually try to boot DOS on it in a little bit, and we'll see how that goes. So if you're not familiar with 4th, it is a very stack-based language. So if we put a few things on the stack, like I'll put 1, 2, and 3 on the stack, we can pop them off and read them one at a time. So we'll get the head of the stack, which will be 3, 2, 1. If you want to do an operation, like let's add 2 and 3, I'll do a 2, a 3, and a plus. And then let's take that result of that and multiply it by 4. So 2, 3 plus, and then 4 times. And that should be equal to 20 if I've done my math right. So we got it okay. Let's see what's on the stack. 20, there it is. So, any operation will pull some things off the stack and put some other things onto the stack. Now you can define, so it does have a built-in vocabulary of many built-in words. So actually plus and times are words in Forth. So let's do words. And you can see everything that it knows how to do. And like I said, there's plus sitting in there, and there's times up there. But you can define your own words as well. So for example, I could do Scott, and let's do this word here. This dot quote means print something. Scott. Here, we'll do something else. We'll just do this as a test. Test of the OEM-188 computer. Then we close off the end of that string, and then the CR word will print a CR, and then semicolon will terminate the definition of that word. So now we have a new word in the vocabulary list called Scott. It's going to scroll off screen, but if I do words, see, it is just kind of scrolling by very fast. It was up there at the top of the list. And if I type in Scott, it prints out this is test the OEM-188 computer. We can also do a simple loop, which is, let's do my loop. And we'll do from 10, counting up to 10, starting at 0, do Scott loop colon. And then we could run my loop. Yep, so it printed out 10 times. And okay, and it might seem like the capabilities that I've demonstrated here are pretty basic, but you can actually do quite a bit and develop very complex programs with Forth. So another computer that I'll be demoing in maybe a few more videos will be the Jupiter Ace. And the Jupiter Ace actually has, complete games written in the Forth language. So it's really quite powerful, and it is quite efficient of a language as well. Now, a lot of these words that they have designed are above and beyond the standard Forth words. So for example, they have some words in here, WBIOS and RBIOS, that seem to do BIOS calls of some sort. I don't know. I don't have the documentation. That's one of the reasons I'm doing this video, is hope that we can get some documentation. Now, there are words in here for interacting with the disk. I think that would be your write block and read block. There's words for programming the EEPROM. That would be your program word. And this EEPROM word, not sure of how it relates. I know there's also a disk word, and maybe the disk and the EEPROM words control whether the built-in editor goes to the disk or the EEPROM or the RAM, because there's also a RAM word. But again, a manual would be really helpful for this. So I will capture in a terminal program the whole list of words for anybody who's interested in that. Okay, I switched over to the terminal program because it's a little bit easier for me to paste code, and it's probably easier for you to read and see what's going on as well. First, I'm going to start with a program called brute prime. Let me just paste it in. Just to be nice, I'll do one line at a time. It's only 3 lines long, actually 3 words long in Forth. And this is my self-described world's worst prime number generator. I like to use it because it gives a very visible output that's kind of easy to put side by side with another instance of it running on something else and get a performance comparison. So let me run brute prime. So this is going to invoke the brute prime word, which is going to invoke the banner word. And then it's going to do, for about 252 numbers, it will check each one of them using this check function, which is itself a recursive loop. So, and then boom, it's gonna output all that into the window here. And it gets slower as it goes. It actually made it all the way up to 255 relatively quickly. Okay, next let me try the Towers of Hanoi. Now this is a demo that I got off of Rosetta Code, which is a great website to go to if you're looking for code samples in a variety of languages. So I'll go ahead and paste it into the terminal. Now, I did have to make a few modifications. Here, let me hit return. Okay, now I did have to make one small change to the Rosetta code before I could get it to work on here, and that has to do with this recursive keyword here. It was just called recurse in the Rosetta code sample, but this dialective fourth uses recursive and then the name of the function. And the reason to do that is you normally can't call a function while you're defining it. You'll get an error that the word does not exist. So I think this recursive word is letting the fourth compiler know that, hey, I do actually want to call the thing that I'm in the middle of defining. And that's how we'll do Towers of Hanoi. Now, if you're not familiar with Towers of Hanoi, it's a relatively famous computer science problem. You've got 3 pegs with different sized disks on them, and you want to move all the disks from one peg to another peg, but you can only stack a smaller disk on top of a bigger disk. So it's a typically recursive algorithm is how you do that. So if we do, let's do 3 Hanoi. And it tells you move a disk from the left to the middle, the left to the right, the middle to the right, etc. And you will, by following those moves, you'll end up moving all the disks to the right places. Now, if we go out further, let's try like 7 Hanoi. It'll be many more moves, and then you're finally done. So let me try a little bit more interesting demo. Let's go ahead and do a cold restart. And now we're going to do Conway's Game of Life. Let me start pasting it into the terminal. This is another Rosetta code demo. This one did take a lot of modifications to get it to work because there were a lot of words that were in the Rosetta code example that weren't in this fourth dialect. So like the value word, I had to redo that. There was just a lot of minor nits like that had to be changed. And again, that's an example of, not every fourth is sort of equal. There are all these little differences. So Conway's Game of Life is a cellular automata. It has a very simple set of rules for you play it on a grid, and depending on the number of neighbors, your cell will either die, stay the same, or multiply. So let's just run it using a well-known initial state called the glider, and we will see there. Okay, it has drawn our glider up here, and each time it will update the generation. So this is a 64 by 16, so it's recomputing the grid each time based on the Conway's Game of Life rules. And this glider will sort of slowly move its way across the screen. There, I sped it up for you so you can kind of get an idea of what it looks like. This does run pretty slow, and I was actually going to use this as my example of, look at how efficient it is to execute fourth programs. But it's running kind of slow, so it really doesn't drive the point. I think part of this is that the Rosetta code examples, they're optimized for clarity, not optimized for speed. So there are, for example, fourth words that all they do is call another fourth word, which is great for making it clear how the algorithm works. And while the fourth calls are really fairly efficient, they're still not free. So there's a lot of overhead that I think if you wanted to make this go faster, you could optimize out and get this thing working faster. I'll leave that as an exercise for the viewer if you want to write a faster fourth version of Conway's Game of Life. Okay, I've had some success getting this to boot some versions of DOS. So I tried both with my physical 360K floppy down here. That was a little bit more trouble. This was an FD54B. Sometimes it boots, sometimes it wouldn't. I switched to using the GoTech because it's a lot easier to have multiple images and to try multiple boots. And I currently have it booting here a Compaq image, which you can see is up on the screen. Now let's see if it's in good enough shape to actually, well, it wouldn't actually do a dir. And it is actually, reading the disk. There we go, that time it did a dir. And, what is words? Oh. Yeah, see that one is not working. There we go, now we've got random hex stuff displayed on screen. Let's go to image 0. I think this is an Epson image. Got loading system, so it got the bootloader, but then it crashed while reading the first track. We've got a loading system, non-system disk or disk error, so yeah. Okay. That time we booted, I replaced a 74 LS540. I'm skeptical that's going to fix anything, but it is working again. What was I doing? I was trying to type words, which I'm betting is not a fourth file, even though it's called words. I'm betting it's just a word processor thing. Yeah, a few words about disks and diskettes. And I think it's crapped out on us again. Try it overflow. My guess is it's a floppy controller where the problem is. Okay, in conclusion, I hope you enjoyed the video on the OEM-188 single board computer by Vesta Technologies. And if you do have any resources, please comment in and let me know. Or if you had one of these, and even if you don't have any resources, if you just have any experience with this thing, or even if you're just a radio electronics reader who just wanted to build something like this, respond back, let me know, and we'll have an interesting discussion. Thank you. Thank you for watching my video. Please visit my website at www.smbaker.com for more electronics projects and sandrail stuff. Bye.